Hello and welcome to lesson 13 on rules of differentiability. So today you're going to be learning some differentiation rules and using them to differentiate functions. So if you remember in lesson 10, when we first started this unit, I told you right now we're starting with the limits, but soon you're going to be learning some rules that are going to help you find derivatives a lot faster. And so that's what we're now starting. So I promise it's getting a little more fun from here. And now we're going to learn some rules. And as we continue this unit, we're going to be learning more rules. So um, I'll show you what the rule is, a proof of it, and then you'll be able to start using it to find derivative functions a lot faster. So starting with our first rule, we have the constant function rule. So if you have a function f of x, which is equal to k for a constant k, and k is any real number, then we say that f prime of x, so the derivative function, is equal to 0. And throughout this lesson, I'm going to show you both notations of the Lagrange notation and the Leibniz notation. And keep in mind here, this is just f of x, so dk by dx is equal to 0. Now, the proof of this one is actually really simple. So consider the f prime of x and its definition with limits. So limit of h approaches 0 of f of x plus h minus f of x. But considering this is a constant function, f of x plus h and f of x are the same thing. They're just k. So k minus k is 0, and we don't have any h here, so this is just 0. Now, let's practice here. So here we have f of x is equal to 7. Then its prime, or its derivative, f prime of x, would just be 0. Another example would be y is equal to pi, and we say dy by dx is 0. And keep in mind here, another way you can interpret this is I don't have any x in here. So when I'm finding the derivative with respect to x, there's nothing for me to differentiate. So then I just end up with 0. Okay, and if we interpret this graphically, so let's say this is y equals 7, or f of x is 7, then this is the rate of change here is 0. So we're not actually changing. So we just say the derivative is 0 because the rate of change is 0. Next, we have our power rule. So you actually already saw this. You just didn't know you saw it. But if you have a function of the form f of x is equal to x to the power of n, where n is a real number, then the derivative is f prime of x, and all you do is bring that power of n and multiply it, and then just take away from the power by 1, so n minus 1. In Leibniz notation, we have same thing, but d of x to the power of n by dx is n times x to the power of n minus 1. The proof of this one, and these get a little bit more complicated, but if you start with that definition for x to the power of n, then here when you have x plus h to the power of n, and this has to do with just expanding the polynomial, which is a bit complex, but you'll end up with all the powers here. And all the powers, and then they would have the h in there, which h is 0. And so if you simplify all of this, you will end up with the x to the power of n minus 1 n times. So then you have the n multiple and then x to the power of n minus 1, or the n coefficient times x to the power of n minus 1. And I'll show you first the examples we already saw. So we already saw for f of x is x squared, that m, which is equal to f prime of x, is 2x. And then another time I also showed you that for f of x is x, or maybe let me show a different notation. Y is x cubed dy by dx is 3x squared. And that's exactly what we are doing here. The 2 becomes a coefficient, and then 2 minus 1 is just 1. And same with here. 3 becomes a coefficient, and 3 minus 1 is 2. Now let's do a few other practices here. So given x to the power of 7, then we have 7 as a coefficient, and x, 7 minus 1, but this is f times x to the power of 6. Now you can actually do this also for functions such as 1 over x cubed. If you remember from exponent laws, this is the same as x to the power of negative 3. So then the derivative of this will be negative 3. All I'm doing is just making my power in coefficient, but then in my power I have negative 3 minus 1. And this is now equal to negative 3 x to the power of negative 4, or negative 3 x to the power of 4. And from our definition above, n is any real number. So I can even do it when I have a power of a power that's a fraction. Now, notice this different notation here because I have s is equal to t, so my input variable is t, my output variable is s, so ds by dt, and again, the power becomes, the exponent becomes the coefficient. Now, in our exponent, we have, and this is just 3 over 2 and t half, or okay, and last one, and this is a special function as well, but here, this is x to the power of 1, right? So when you bring the power down, we have 1 and x, 1 minus 1, but this is just, and I won't rewrite the 1, x to the power of 0, which is equal to 1. And this is just our linear function, right? Y equals x. And so it's clear that the slope of the tangent will just be 1, and the rate of change is changing at a rate of 1. Now we have our constant multiple rule. So this tells us that if a function f of x is k times g of x for another function, and k is a constant here. So again, k is any real number here. Then the derivative of f of x, or f prime x, is given by k times the derivative of g of x, so g prime x. Or in other words, if you have y equals k, the function f of x, which can be ky, then the derivative of this is the derivative of the y, and the k as a constant does not really affect our derivative. Like it just stays as a constant there. Now the proof of this one's a little simple as well. If you start with your definition of a derivative based on the limit, then substitute that f of x is k times g of x. Here we have k times g of x plus h and k times g of x. But here I can just factor out the k, and this has to do with my limit rules as well. And then I have g of x plus h minus g of x over h. But keep in mind, this, oh, maybe let me highlight it. This is actually g prime of x by definition. And so by limit laws, if I bring that k out and I have that limit, then I actually just have g of x, exactly, right there. Then f prime of x is k, this is the k, and this limit is now g prime of x. Now let's see what that would look like here. So this, I would write f prime of x here. And this is just, so I'm going to leave my 7 there, and I'm going to take the derivative of dx cubed by dx, which by power rule is 3x squared. And this is just 3x squared, which becomes 21x squared. Now for this next one, again, we start with, I'll just leave the 12. And now I'm going to find the derivative of d of x to the power of 4 over 3 by dx. And by power rules, we have 4 over 3 x 1 over 3. And this will just go here exactly as is. And here we just have to simplify to get 16x to the power of 1 over 3. Our next rule now is the sum rule. So the sum rule tells us that if we have two functions, p of x and q of x, and they're both differentiable, and we also have f of x, which is p of x plus q of x, so keep in mind sum, then f prime of x is p prime of x plus q prime of x. So you just take the derivative of each one individually and add them because they're just being added here, so you add them here as well. And now in Leibniz notation, d of f of x by d of x is equal to d of p of x by d of x plus d of q of x by d of x. Okay, so again, just the derivative of each one. Now, to see that with our definition of a derivative, so taking that limit, f of x plus h is just going to be p of x plus h plus q of x plus h. And f of x is just p of x plus q of x. Now here, we can split this. So we have the two parts with the p of x and p of x plus h together, and q of x plus h and q of x together. Now, if we remember limit laws, because this is a sum, I can take the limit of each of these individually, and this by itself, in definition, is the derivative of p, so p prime of x, and this by definition is the derivative of q, and q prime at x. Now, I don't have a definition. Okay, wait. I'll give you an example here for this. So consider f of x is x cubed plus 4x. So f prime of x is going to be the derivative of x squared, which now we know by power rule is 2x, and the derivative of 4x. And this has two parts. This is first the constant rule. You take out that k, which is 4. And now d of x by d of x was just 1 as one of our special functions. And we're left with just 4 there. And that would be our derivative by the sum rule. Similarly, we also have the difference rule. So the difference rule, very similar, but now we just have a difference. So if for those two functions, p of x and q of x, which are both differentiable, we have f of x, which is p of x minus q of x. Then the derivative of f of x, so f prime of x, is p prime of x minus q prime of x. And here we also have the Leibniz notation with shown as d by dx. Now, for the proof, I encourage you to try, especially because it's very similar to this. Now you just would have a difference. So instead of the addition. So here you would have a difference, and same here. And then you'll see how this distribution there will affect your final answer. And you should end up with p prime of x minus q prime of x. Now here I put two examples of both of those for you. So in the first one, we have 2x squared. So we take the product rule there to get, and it's a mix of the product rule and the constant rule because you have the 2 there. So think of it first as I keep the 2 there, and then for x squared, that's 2x by the power rule. And same with here, the second one. So I have that difference there. Then I keep my constant, which is 5, and now I'm looking for this value. But keep in mind that square root of x is just x to the power of half. Now, taking the derivative by the power rule, move this up. This is just half, and then x half minus 1, which is negative 1 over 2, or in other words, 1 over 2 square root of x. And now I just substitute this back because it's just a constant rule. So we are left with of x. And if I just want to write this a little bit more neatly, this will be 4x minus 5 over 2 square root of x. Now in this next one, you see this and you think it's the product rule, but not quite because you have a function in there. And we haven't seen just yet. There is another rule which will help us differentiate this. But as of right now, we have to first expand this. So 3x plus 2. And this will give us, or if you remember that a plus b squared is a squared plus 2ab plus b squared. You can also apply that, but just as an expansion, it'll be the same answer. We have 9x squared plus 12x plus 4. Now here I have 3 terms, and think of this as f1 of x is 9x squared, f2 of x is 12x, and f3 of x is 4. And I'm applying the sum rule here. And let's just find the derivative of each of these. So 9x squared, I keep my 9 there. And then by power rule, I have 2x. So this is 18x. In the second one, this would just be 12. I hope you see that now from, especially because we did the example above. So dx by dx is just 1. And for the last part, I have 4. So the derivative is just 0 by the constant rule. So then I'm left with 18x plus 12. And that's my derivative there. And so again, like I mentioned, right now, because you don't, you have a function within the bracket. So this is actually probably, we would say f of x is g of x squared. This is not the same as the power rule. So if we go back to the power rule, keep in mind, this is x to the power of n, which is not what we have here. We have a function raised to the power of 2. And so you, again, like I mentioned, you're going to see later on how to work with this, but we don't have that right now. So you have to do the expansion part and find the derivative using the sum rule for each of the terms. Now, see a little bit of application. We've done a lot of algebra and theory, but we're now going to be connecting the concept of derivatives to a real example. So derivatives can be seen as velocity, or again, the instantaneous rate of change. And the position s in meters of a moving object after t seconds is defined by the function s of t, and it's t plus 2 squared. And you're asked to find the velocity of the object after 3 seconds. So we want to find the derivative at a specific point, and the point being t is 3. So we first want to find that derivative function. And again, like I mentioned, because this is a function squared, you cannot apply the power rule just on its own. So we have to expand. And if we expand, we get s of t is equal to t squared plus 4t plus 4. Now, by the sum rule, and here I'm showing you with Leibniz notation, ds by dt is going to be each of those, the derivative of each of those terms. So dt squared by dt, dd4t by tt, and d4 by dt. So first, the power rule tells us for this part, we have the exponent becomes the coefficient 2, and our new power is 2 minus 1, so just 2t. For the second part, the constant multiple rule tells us that the derivative of 4t, we can factor out the 4 so that we're actually just finding dt by dt, and same with dx by dx, this is just 1. So then our derivative here is 4. And finally, the constant rule tells us that d4 by dt is just 0. So putting this back into our derivative, we have 2t plus 4. And now we want to find, and keep in mind this was velocity, and velocity can be written as v of t. This is, or sorry, v prime, or no, v of t or s prime of t. And this is now exactly s prime of t, 2t plus 4, and after 3 seconds, we just substitute to find 2 times 3 plus 4, which is 10 meters per second. And yeah, that's our now real life application of derivatives. We can see that it helps us find the instantaneous rate of change. And throughout this unit as well, you're going to see other applications. So hopefully that makes more sense of why derivatives are important. For our next example, we're going to be using derivatives to now find the equation of the tangent line, and it'll be a lot more simpler now. And keep in mind, we are asked to find it in standard form, so we'll make sure our final form is in standard form. And you're asked to find the equation of the tangent to the curve y equals x to the power of 5. And you're already given the point here, but if you were just told x is negative 2, then you would just find that y at negative 2, so f of negative 2 is just negative 32. So to find the equation of the tangent, and again, remember we want to find the derivative function so that we just have it. And if we're asked to do any other work for this question, we already have the derivative function ready to go. And now using our derivative rules, it's a lot faster. So to find dy of dx, we apply the power rule here. So the power rule tells us that 5 is now our coefficient, and we have x to the power of 5 minus 1. So this is 5 minus 1, which is 4. And f prime of x is 5 times x to the power of 4. Now, the slope at the point negative 2, negative 32, is found by just substituting the x value, which is negative 2. So m is f prime of negative 2, which is equal to 5 times, and here, the 16, this is just negative 2 to the power of 4. And we find that this is 80. And now we're just finding the equation of a linear line. So we have our slope is 80, we have the point, and all we have to do is find b. So our y is equal to m times x plus b, and we get that b is 128. So our function is our linear equation of the tangent is y equals 80x plus 128. But we were asked to find it in standard form. So standard form, all we have to do is just move all our terms to one side. So we have something equals 0. And so if we do that, we have y minus 80x minus 128 is equal to 0. And that's the equation of our tangent to the curve y equals x to the power of 5 at the point -2, -32. Okay, so just to wrap up our lesson, so at the end of the next few lessons, you're going to see these rules of differentiability. So far we saw power rule and the sum and difference rule. So I've added them here for you as kind of like a resource, and all the other ones we learned, I'm going to keep adding. So each lesson check at the end, and you're going to see the most updated version with all the new rules. And that's our wrap on our lesson. So you have some practice problems here. And as always, check Google Classroom for some additional tasks. And if you have any questions, don't hesitate to reach out, and I'll see you all next class.